started. So section 4 is the completeness axiom. Right, and so this is the axiom that distinguishes. This is the fact about the real numbers that distinguishes it from the rational numbers. This is what makes the real numbers the real numbers. In some sense, this is how you construct the real numbers from the rational numbers. Okay, so you start with something simple idea, and that is the notion of maxes and mins, right? So if you have a subset in R and S is non-empty, right? If there exists some S naught in S such that S naught is bigger than everybody else, right? If there's somebody in there where S naught is bigger than everybody else, we say S has a maximum. Okay, that S naught is the max of S, or the max of S where S neighbors over S. The max of those guys. Okay, and similarly, right? Similarly for minimum. Okay, so right, and so the example or the question I put up last time we were finishing up with was this: any finite non-empty set S in R has a max and a min. Max and a min. Okay. If I say 1, 2, 3, 4, 5, right? Well then, 5 is the max and 1 is the min, right? And those guys are in your set. Right. Max is 5, right? And the min is 1. Right. And I asked, how do we know this is true? And Raleigh said, well, if you suppose you take any finite non-empty set in R, and you order it using the ordering, right? You use your ordering on it. There's going to be some least element there, right? There's going to be some least element there, and that guy's going to be your minimum. So that's how Raleigh proved it. That's actually sort of I should say that's actually using an assumption that's called the well ordering principle. Well ordering principle that if you it basically says that if you have any non-empty set. It's basically saying this, that if you have some non-empty set of then there's going to be some least thing. That actually to prove that actually you need to use induction. So to get the well learning principle, you actually use induction. So it may be not as, it seems like it's an obvious statement to make, but it's actually a consequence of induction. Okay, just to be careful. Okay. That's actually a consequence of induction. Just to give you, so just for a digression, to give you another thing that might seem completely obvious, but actually turns out to be quite subtle. How many of you have heard of the axiom of choice? The axiom of choice. Mia, yeah. Do you know how do you say it?
Is it the one for a geometric field, or it's like something about a line and then the dot and you can't cross or something?
No. It's something different. So axiom of choice has to do with it's the following statement: given any collection of sets, given any collection of sets, it's possible, roughly speaking, one can choose an element from each set. One can choose an element from each set. So it's possible to, like if I have some infinite collection of sets, it's possible to choose one element, A sub alpha, from each set. Okay. How many of you think that seems obvious? Does that seem obvious? If you have a bunch of sets, it's possible to choose one element from each set. If I have two sets, is it possible to choose an element from each set? Yeah? Right? You should. What was the only one with the expression I'm looking for? You should all be circling. Yeah. Doesn't this seem completely obvious, right? That if you have a set, you can choose an element from this set.
But what if that's an empty set?
Oh, I'm sorry. They're non-empty sets. Thank you. Yeah, they're not empty. Okay. Now does it seem like, of course that's true? You're all okay. Maybe you're all suspicious at this point. None of you want to say, "Of course that's true," because you know that I'm going to say that it's not so obvious. Right? Okay. Yeah. So, okay. This thing seems completely obvious, but in fact, if you assume this, and so I should say, most mathematicians assume the axiom of choice, that you're allowed to do this. Okay. But there are mathematicians who say, no, we're not going to assume the axiom of choice. Or at least there used to be. I don't know if there are many anymore. But at one point in time, it was sort of like, are we going to take the axiom of choice as one of our basic, fundamental axioms, or no? And in the Princeton math hall, I saw a picture of one of my old professors as a graduate student. So he was my professor at the time, but I found his picture there as a graduate student. And he was there, and he's wearing this T-shirt, and it says, "Support the axiom of choice." In the 60s or something like that. Anyway, so this is something that seems completely obvious, right? Like, oh, of course you can do this. But there's some strange things that happen if you assume it. In fact, if you assume it, if one allows the axiom of choice, some bizarre things happen. Some bizarre things happen. In particular, there's one which is really famous called the Banach-Tarski paradox. Okay, there's something called the Banach-Tarski paradox. And what it basically says is that you can take an orange, okay, and you can cut it up into a finite number of pieces. Okay, a finite number of pieces. And then you can rearrange those pieces and get two oranges of exactly the same size. Okay. So you can take an orange, I'll say it again, you can take an orange, cut it into a finite number of pieces, take those pieces and put them back together and get two oranges this time. Okay. And that actually happens if you allow the axiom of choice, then you allow the Banach-Tarski paradox. Okay, so you can see why some people would say, no, in that case, we don't want to allow the axiom of choice. Okay, because you get some strange things occur. Okay. Anyway, this is just to give you an example of things that you think, oh yeah, of course you can do that, but you have to be a little bit cautious. Okay. Okay. So any finite non-empty set has a max and a min. You can prove by induction. We actually proved this by induction earlier in the course. Right? Or you can basically use induction here. Okay. Okay, okay. So, what if, you know the answer to this question, what if S is infinite, is an infinite set? You know, must it have a max? Must it have a min? And somebody, what's the answer to this? Those of you read the book, what's the answer? The answer is no, right? Give me an example of an infinite set without a max, without a min. N. So N has a min, has no max. Right? Or Z, say, has no min and no max or min. Right? A little bit more subtle, can you give me a bounded set? A set that doesn't go off to infinity, but has no max and no min?
Sorry, does N have a min?
Yes, right, because it's 1, 2, 3, etc. There's an element which is smaller than there's an element in the set that's smaller than equal to every other element in the set. Okay, can somebody give me a more subtle example? So these guys go off to infinity, right? That's why they don't have, this one goes off to infinity, doesn't have a max. This one goes off to infinity, negative and positive infinity, that's why it's no max or min. But what about, can you give me a set between here and here that has no max and min? Okay.
Negative root 2 and root 2.
Okay, so you could say the set from negative root 2 to positive root 2. The open set, say, right? Has no max or min. Right? What about Edwin?
Can you expand on that?
Yeah, sure. So what about this set? Does this set have a max or min? This set does, right? This set does. So, right, so the point is that if you have an open set, we don't have to use root 2s or anything. We could use 0, 1. Just to, the fact that the endpoints are irrational is not necessary. Okay. If I look at 0, 1, the open set 0, 1, the open interval 0, 1, is there a point in here that is bigger than or equal to every other point in here? Well, the answer is no, right? Like if I say, this is the max. Well, you would say, what? I can find a point between here and 1. I can find a point between here and 1 that's bigger. So that's not the max, right? And no matter what point you choose, there's always some element that's bigger, right? No matter what point you give me, if you're going to tell me that there's a max or a min in here, what is it? No matter what point you tell me, I can find something bigger, and I can always find something smaller, right? But for this one, 0, 1, if you say 1 is the max, you would say 1 is the max, and I would say, you're right, I can't find anybody bigger than 1. Okay. So this set has no max and min, this set has a max and a min. Okay. Okay, is that clear? Okay, so these examples lead us to the following definitions. There's some language that we'll need. If you have non-empty sets in R, if you have a non-empty set in R, if there exists an M in R, if there exists a real number such that S is less than or equal to M for all S and S, and we say S is bounded above. And call if there's a okay, and similarly for lower bounds, similarly for bounded below, and lower bound. Similarly for bounded below and lower bounds. Okay, and if S is bounded above and below, we call it bounded. Okay, so going back to these guys over here. I'll wait for a second. Looks like people are ready. Okay. Going back to these sets over here, right? This 0, 1 is bounded above and bounded below. This is bounded above and bounded below. Right? What about this? It's not bounded above and it's not bounded below. What about n? Is it too obvious? Mia, tell me what it is.
It's bounded below.
It's bounded below, but not above. Right? Okay. So that's the notion of boundedness. Emily, yes?
Yeah, you said for 0, 1, that's,
It's bounded. Yeah.
can you explain why?
So what does bounded mean? So bounded above means that there's some number. So you have some set. Here's your set. Okay. If there exists some number m such that for all elements of your set, m is bigger than. Okay. So m for no matter what s you choose. There are a bunch of s's there. You can choose this one, this one, this one. But m is bigger than all of them. Okay. Then this guy's called an upper bound of your set. So this thing here is my set. All these things together are my set S. Right? There's somebody that's bigger than every element. That's called an upper bound. Okay. And you notice that if you have one upper bound, certainly you have more. You've got other upper bounds. Right? There are a lot more upper bounds. Okay. Right. If there's some little m that is less than everybody, then that guy's called a lower bound. Right. If you have an upper bound, you call it bounded above. If you have a lower bound, you call it bounded below. If you have an upper and a lower bound, you call it bounded. Okay. And so here, you've got the set 0, 1. Right? From 0 to 1, it's just this, right? 1 is an upper bound. 2 is an upper bound, right? 0 is a lower bound, negative 1 is a lower bound. Right? You have upper bounds and you have lower bounds, so these guys are bounded sets. Right? But n, it's not right for n. Right? There's no m that is bigger than everybody. Right? Whatever m I choose, there's going to be some natural number that exceeds it. Right? At some point, the natural numbers will exceed it, right? But I could take, but 0 works as, I guess I'm counting from 1. 1 works as a lower bound, right? 1 is the lower bound for this set. Okay. Everyone all right? Okay. So those are easy ideas. Okay. Now comes the important idea. Okay, now comes the crucial idea. So the critical definitions are the following. So again, you have some set in R, some subset of real numbers, and non-empty. If there exists an upper bound m naught of S, such that for any upper bound of S, for any upper bound m of S, m naught is less than or equal to m. Then we call m naught the least upper bound. Of S. Least upper bound, also called the supremum. I like the terms least upper bound better than supremum, but you should know the term supremum. Okay, and similarly, there's something called if there exists a lower bound. If there exists a lower bound, that is bigger than or equal to every other lower bound, then we call it the greatest lower bound. It's also called the infimum. Okay, so going back to our examples again, right? If we look at, I'll wait for a second. Okay, going back to our examples again, right? So this set 0, 1, this set 0, 1, has a bunch of upper bounds, right? 2, 3, you can use any of these numbers. 1 is also an upper bound, right? But there's no upper bound that's less than that, right? There's no upper bound that's no upper bound that's less than 1, right? 1 is the least upper bound. Okay, 1 is the least upper bound, so 1 is the supremum of the set 0, 1. Right, 0 is the infimum of the set 0, 1. Right, the least upper bound, the greatest lower bound. Okay. And okay, is that clear? It's not too complicated an idea, right? We have upper bounds. Now we're saying we're gonna if there is an upper bound that is less than or equal to all other upper bounds, we call it the least upper bound, right? If there's a lower bound that's bigger than or equal to all other lower bounds, we call that guy the greatest lower bound. Okay. And now we come to the main thing, right? Here's the completeness axiom. Also called the least upper bound axiom, right? Again, we have a non-empty set S that's in the reals. If S has an upper bound, then S has a least upper bound in the reals. So we're assuming that we're in the reals. Any set with an upper bound has a least upper bound. Right. So in R, any non-zero set, non-empty set with an upper bound has a least upper bound. Okay. So you're guaranteed a least upper bound, and this is the fact that Q does not satisfy, right? The rational numbers Q does not have the field of rational numbers. Field of rational numbers does not satisfy this. And I should say that this is an axiom. This isn't something that we're going to prove about the real numbers. It's actually basically something that is used to create the real numbers. Okay, so you don't prove the least upper bound axiom. Just like you don't, when you're talking about, you don't prove the commutative property, right? That's part of the commutative property is part of the definition of your of the rational numbers, say. Okay. So you don't try to prove this. Okay. So you read the book, right? In Q, the set of numbers whose square is less than 2 has an upper bound, has both upper and lower bounds, but no least upper bound and no greatest lower bound. If we were back in the days of Pythagoras and our field was Q, we wouldn't think this was a reasonable thing to say. Right? This would not be a property of our numbers. Rather, we'd say, oh, you can have upper bounds, right? Well, we'd say, well, I'm looking at the set here. Here's my set S, and I can find upper bounds for it, right? Certainly 2 is an upper bound for it, right? And I'd say, well, 2 seems to be an upper bound for this set. 1.5 seems to be an upper bound for this set. 1.42 seems to be an upper bound for this set. And you'd be able to find like an infinitely decreasing sequence of numbers that were all upper bounds, but none of them would be the least, right? There would be no number there that is the least upper bound in that, if you lived in that world. Okay. But in the real numbers, there actually is a number that is the least upper bound, the square root of 2. Is it everyone getting a sense of what the least upper bound and greatest lower bounds are? Maybe I'll make you do an exercise to make sure that you do understand. Okay. So here's an exercise for you. Suppose again S is a non-zero, non-empty set that lies in the reals. Suppose S is bounded above, and the least upper bound of S is not an element of S. Suppose you have a set, it's bounded above, so it has a least upper bound, but that least upper bound is not part of your set. Then, for any positive number epsilon, the integral least upper bound of S minus epsilon, least upper bound of S must contain an element of S. Think about that just for a minute and see if you can understand what the problem is saying. That's the first part. Right? Do you understand what the problem is saying? So take a minute and see if you can draw a picture of what this means to you. Or give an example or something. Okay, let me just sketch how you might think about this. Okay, so you have some set in R. You have some set in R, so you say, okay, you have some set in R, it's bounded above. Right? It's bounded above, and so we know that there's a least upper bound, so this guy is going to be least upper bound of S. Okay. Least upper bound of S is not an element of S. So not an element of S. Okay. It says then for any epsilon, the interval least upper bound minus epsilon, least upper bound, this open interval here has to contain an element of S. Okay, so that's saying that if I look at any tiny interval of length epsilon, then the interval least upper bound minus epsilon, comma least upper bound, there must be somebody in here that's an element of S. Okay, so right, if I have some set like this, suppose I have these guys coming up to 0, like -1, -1/2, -1/3, -1/4, -1/5, etc., right? These guys are approaching 0. Just to give it a concrete example, right? This thing here is the least upper bound of S, but none of these guys, S is not in there. S is not in there. And what we're saying is that no matter how tiny an interval you take, the claim is that no matter how tiny an interval you take, from 0 minus epsilon to 0, right? No matter how tiny your epsilon is, there's going to be some element of your set in there. Okay? There's going to be some element of your set in there. And you see that that's true, right? No matter what epsilon I take, well, there's going to be, one of these guys is going to, in fact, infinitely many of these guys are going to be in that interval. Okay. Okay. And so the question is, how do you prove that, right? How do you prove that? I think I'll put this on your homework. I'll put it on your homework. No, I'm going to put it in. People are shaking their heads, but I'm going to put it on your homework. Okay, but I'll give you a hint. The hint is proof by contradiction. Proof by contradiction will make it pretty straightforward. Right. Suppose suppose that this fails, right? Suppose this fails. Suppose that there is some bad epsilon, and in that, with that bad epsilon, then this interval contains no elements of S. So proof by contradiction, suppose there's a bad epsilon. Right? The claim is that for every epsilon, you're going to have something good happen. Suppose it fails for some epsilon. Okay, and see what happens. Okay. Okay. Consequences of the least upper bound axiom. One simple one is something that could be called the greatest lower bound axiom. Okay. If it's not called this, but you know, it would make sense to call it this. The greatest lower bound.
Sorry.
Yeah. Yeah. Could you shut the door?
Yeah.
Thank you. It's okay. Just not awake. Okay. Okay. So if you have a set, again a non-empty set in R, if this set has a lower bound, then what am I going to say? If you have a set in the reals that has a lower bound, then it'll have the greatest lower bound, right? It has a greatest lower bound in the reals. Okay, so you don't assume this. This is not an axiom, right? The least upper bound axiom is assumed, and from it you can prove the statement about greatest lower bounds. Okay. You don't need to assume the greatest lower bound axiom because it's a consequence. It's an immediate consequence of the least upper bound axiom. So, does anyone know how to do it? Some of you have read the text, I'm sure. All of you have read the text. Does anyone know the trick? What's the trick? You have some set, and it's bounded below, right? It's bounded below, and you want to show that there is a greatest lower bound. You have already the least upper bound axiom, which is that if you have a set and it's bounded above, then it has a least upper bound. So what's the trick? How do we take this problem and then change it into a least upper bound problem? Well, flip it over, right? Flip it over. Multiply everything by negative 1. And then you're going to have a set which has an upper bound, right? Its upper bound will be negative m. You're going to have the set negative s. Its upper bound will be negative m. And because it has an upper bound, right, so we flip it, we get the set negative s, which has an upper bound, negative m. Now we can apply the least upper bound axiom, right? So that will have a least upper bound. Flip that guy back, that will be your greatest lower bound. Okay. So the idea is simple, right? You think, okay, I want to use my previous statement. So how am I going to do it? I'm going to flip it over and do it. So, so the idea is like this, right? Let negative s denote the set of all negative s where s is an s, right? So it's the flip going to be the flip of S, right? Since M is less than or equal to S for all S in S, right? So there's a lower bound, call it M. Since M is less than S for all S in S, we have that negative M is going to be bigger than or equal to negative S for all S in S. Right? In other words, negative M is an upper bound for the set negative S. Right? By the least upper bound axiom, it exists, since negative S has an upper bound, it has a least upper bound, right? There exists some number, there exists a least upper bound of negative S, call it S naught. So there exists some guy up here, call that guy S naught. There exists some least upper bound. And then you need to show that negative S naught is the greatest lower bound of S. Okay. Which I'll leave as an exercise.